This content is AI generated for informational purposes only and should not be directly used for clinical decision-making.
Hello, and welcome back to the Neurosurgery Hub podcast. I'm Dr. Aris, Senior Attending in Neurosurgery.
And I'm Dr. Alara, Research Fellow. Today we're looking at a fascinating new study from the journal NeuroImage, published in 2026, titled Negative Motor Areas, Functional Connectivity Using Stereoelectroencephalography.
This is a topic that often puzzles residents and even some seasoned attendings during cortical mapping. We're talking about negative motor areas, or NMAs. Alara, for our listeners who might need a quick refresher, how does this study define an NMA?
The authors are very specific here. They define negative motor areas as cortical regions that, when stimulated, determine an inability to pursue voluntary movement or sustain voluntary muscle contraction. Crucially, this happens without producing any other symptoms or signs, so no accompanying sensory changes or involuntary movements. It's a pure arrest of motor function.
Exactly. It's that moment in the OR or the EMU where the patient just stops. And historically, we've looked at these as isolated spots on the brain. But this paper shifts the paradigm toward a negative motor network. What makes this particular study a first in our field?
This is the first study to address both the localization and the functional connectivity of this network using the stereoelectroencephalography method, or SEEG, in patients being explored for focal drug-resistant epilepsy. While we've had data from subdural grids, SEEG gives us that unique three-dimensional perspective and access to deeper sulcal structures.
The scale of the study is also quite impressive. They didn't just look at a handful of cases.
Right. They reviewed responses to high-frequency intracranial stimulations in 225 consecutive patients across two different epilepsy centers, one with 115 patients and the other with 110. From that large cohort, they identified 41 specific stimulations that elicited the first overt sign of negative motor manifestations.
And those 41 stimulations were found in 23 patients. That's a significant hit rate when you're looking for such a specific phenomenon. Now, for the residents listening, why does the connectivity aspect matter more than just knowing where the stop button is?
Well, the study suggests that negative motor responses aren't just local effects. By evaluating functional connectivity changes, specifically looking at how these areas communicate with the rest of the brain, we start to see the NMA not as an island, but as a node in a larger integrated system. The paper looks at how these areas are networked to prevent or interrupt movement.
It's about the negative motor network. If we understand the connectivity, we can better predict the risks of surgery in areas that might not be primary motor cortex, but are vital for the fluidity and initiation of movement.
Precisely. The methodology used SEEG to assess these changes by evaluating the H coefficient, though the core takeaway is that the localization of these 41 points gives us a map of where the brain's brakes are located.
And because these were drug-resistant epilepsy patients, these mappings are incredibly precise. When we use high-frequency stimulation in SEEG, we are looking for that specific clinical arrest. If a student is watching a mapping session, they might see the patient asked to perform a repetitive task like finger tapping or counting, and then, during stimulation, the movement just ceases.
And as the paper emphasizes, the patient remains conscious and able to understand instructions. They simply cannot execute the motor plan. This study helps codify those areas across a large population, giving us better statistical power for where these NMAs reside.
It really underscores the complexity of the motor system. It's not just about the go signals from the precentral gyrus, it's about this intricate balance within the negative motor network.
It's a vital read for anyone involved in functional neurosurgery or epilepsy surgery. Understanding that these areas are part of a connected network rather than isolated points will definitely change how we approach surgical planning in the frontal and parietal lobes.
Absolutely. A huge thank you to the researchers for providing this SEEG-based insight into the negative motor network. That's all the time we have for today's deep dive.
Thanks for listening to the Neurosurgery Hub podcast. We'll see you in the next episode.